This work all started when I was at UCLA, and I met with Alex Cunha, who was a postdoc at UCLA like me, and then he moved to Caltech. And we started to do some work with Stan and also other people. And the point of this talk is to tell you what we've been doing and where we could go from here. And hopefully the algorithms that we present today will be useful to you. And if they are, then please let me know so that I can help you with the code and adapt the code for your own application. The idea of microscopy, as it has been exposed in previous tutorial, is that it has revolutionized many aspects of sciences, including new discoveries and contributions to science and technology in general. That has been acknowledged by two recent Nobel Prizes in 2014 and 2017. Oops, I'm sorry. Something is wrong. Okay. Now, even though we have the technology to produce this image, it doesn't mean that the quality produced by this equipment is sufficient enough to extract the relevant information that we want for specific applications. The typical challenges that we have in microscopic images that the amount of noise is generally extremely high compared to other kind of imaging, such as taking a picture with your phone or taking a picture from a satellite observing Earth. The amount of data to process is quite high. These are large images because the resolution is high. So this is a trend that is going on again and again. And we also have very specific features that we want to extract from these images because of applications. And I'm thinking here specifically in biology, where the object of interest that we want to extract could be narrow, thin, like a filament or a bundle of filaments that are very, very thin. By thin, I mean here a few pixel wide. So it means that it is challenging even to see them when you want to visualize it. And it might even be harder if you want to automatically extract those features in these images. And validating the results when you have such problems, especially in biology, may be a challenging one. So one of the aspects of computational scientific computing to try to overcome these challenges is to create fast, scalable, robust algorithms with the purpose of denoising the image so that we can improve the quality of the image for the application, while preserving fiber-like structures. And if we are able to do that, then it paves the way to get compact representation of essential features that are contained in these images. So today, my main goal is to give you a quick overview on how we can create super efficient and scalable codes to create those filters, to process these images. So I want, maybe it is better to give an illustration using images. So this is an image that Alex provided 15 years ago-ish about Cryo-EM. And you see on the left the original image. What you see in the middle is the image after a normalization of the histogram. And on the right, this is the image that you get when we apply the filter that I'm going to describe. What we can see in these three images is that originally you have noise and the contrast is low. If you do the histogram equalization, then you get more contrast, but you see a lot of noise. and it's really hard to see the structure inside this bacteria. And what you see on the right, after the filtering, you start seeing some filaments that are actually present in these images. Another example here is about bacterial filaments. Again, on the left, you see the original image that was captured. Here you see a zoom of this noisy image, and after some denoising, you start seeing some filaments that we expect to see. I have another application about the Nissl strain. About the Nissl strain histological dissection of a mouse brain. So this is the original that you see on the top left. Then after some filtering, you can essentially extract the significant contours of this image. On the top right, I show the difference between this cartoon representation and the original image. And if you zoom in about this process, then you see that we were able to extract the contour, but we still have a little bit of noise. So after another filtering, you are able to correctly extract the contours in this image, which allows you to produce, for instance, a triangulation of the content of this image using only very little memory compared to the original image. So the question is how to do that? Well, we're going to do that using some image processing techniques for denoising. And as it was mentioned in many tutorials, there are many, many approaches to denoise images. So I'm not going to review all of them. Here I give a brief list, and I'm going to focus on the last point that is called non-local means. Non-local means has been introduced by Buades, Coll and Morel in 2005, and it became a really important tool that changed the image processing landscapes using these ideas. And what I'm going to cover today is how to implement these original papers of Buades, Coll and Morel, non-local means, in a much more efficient way than it was originally produced. To be specific, I will show you how to create an algorithm that can be 100 times faster than the original method. 100 times faster means that instead of taking a couple of hours to process an image, you can do it in less than 2 minutes. And then I will show you how the idea of using non-locality in variational methods can be used to extract relevant information in images, and in particular in microscopic images. So the outline of the talk is as follows. There are two parts. The first part is about presenting a super efficient algorithm for implementing the original non-local means denoising proposed by Buades, Coll and Morel. So I will give you the big idea of what non-local means, and I will also tell you the computational limitation of the original algorithm. And then I will show you how you can rewrite the original algorithm in such a way that it will give a fast and scalable implementation of non-local means tailored to modern computing architecture with 100 speed up. And I will also show you some applications of this method to Cryo-EM. And then, following the idea of non-local means, I will incorporate the concept of non-locality into variational methods, and in particular, total variation. And that will yield optimization problems that are known to be difficult to solve, but I will show you how we can leverage graph theory and graph algorithms to optimize these non-local total variation models. And then I will apply it to some biological microscopy. Feel free to interrupt me if you have any questions. So, I'd like to mention two papers that revolutionized image processing. The first one, in my opinion, is due to Stan and his co-author about the Rodino-Fatemi model in imaging sciences. So this is how the total variation was introduced in image processing. The idea of that paper is to formulate image denoising as what we call a variational problem, and after discretization, it yields an optimization problem. And Stan and his co-authors introduce the regularization called total variation that allows to preserve edges in images. So that paper has, as of today, more than 17,000 citations. It has a huge impact and completely changing the way people process digital images. There are, however, some limitations of using this model. It's when your image contains some textures. So when you are using RF model, it tends to remove the texture. So you can see it as a bad feature for denoising, but you can see it the other way. You can use the Rodino-Fatemi model to extract the texture. So depending on what you wish to do, this model is still useful. And if you have also some narrow and elongated feature, the RF model tends to remove those features because it is embedded in the definition of what the total variation is. And total variations are defined using only the nearest neighbor interactions. And this is the main difference compared to the second revolutionary paper of Buades, Coll and Morel about non-local denoising, where this time, these people didn't force a model that comes from mathematics, but suggested that the model that we should use is the noisy image itself that you want to denoise. And the idea is pretty simple, and it works as follows. You select a pixel that you want to denoise, you form a little patch around it, then in that same image, you search for similar patches, and once you found several of those, then you are simply doing the average of those pixels to denoise the pixel of interest. So in that sense, you are looking at similar patches in the image. So in that sense, it is non-local. And how you do the denoising, once you have those patches, you simply do an average. Thus, the name non-local means for image denoising. So one of the key properties of these methods is that you collect information that can be far away from the pixel that you want to denoise. So we call that non-local interactions. And this is in contrast to what people have been doing before when models were using only nearest neighbors in the interaction. So let me show you the idea of NL means on some pictures. So on the left, you have an original noisy image. Then here I represent some patches using squares in colors. So this is what the algorithm detects. Let's say that you have the the red patches, and then you're going to use that information of the red patches to denoise each pixel inside the red patches, and similarly to the blue, and similarly to the green. What you see intuitively is that the NLM method tries to assume that in the image that you want to denoise, you have some repetitive patterns. And the idea of these methods is to try to detect patches where the pattern repeats. And if you are able to find those patterns that repeats itself in the image, then you can get an excellent denoising. And this is what you see on the right, which is a pretty good result when you do image processing. So I insist, the key assumption in NL-means in that it is implicitly assumed that you have repetitive structured pattern, and then you search using windows these repetitive patterns. And you are using the redundant information that is assumed in the image to perform the denoising using a weighted average of pixels in similar patches.
Do you take any questions?
Yes.
So in that context, let's say you were to apply that to bioimaging. Imagine, for instance, like looking at a fingerprint where there's lots of very redundant patterns but rare artifacts. Would that technique tend to erase artifacts and replace them with like redundant patterns, or is this technique specifically preserving artifacts in the context of like nearly identical patterns around them?
Now, I mean, what's going to happen if you do not find similar patches is that essentially you're not going to modify a lot the image. So you're going to preserve the noise.
So in other words, is there a soft criteria for similarity? Because we're talking about images that contain noise. So like, what's the criteria that says similar? It's not exact pixel values. For sure.
I'm going to tell you that right now.
Oh, sorry about that.
But essentially, you should see it as the square of the difference of two patches.
Thank you.
That's it. Any other questions?
Just a comment. I mean, this reminds me, God help us, of AI, where you are using additional information to enhance an image. So now we're not using additional information, we're using information for the same image. But,
yes.
But the procedure is very, very similar to creating an architecture. In fact, it's the same, except...
Yes.
So this had a brief flurry of being incredible until AI came on the scene, I would say.
Absolutely.
Yeah. Okay.
Okay. So let me give you briefly the mathematical formulation of NL-means as it was described by Morel and his co-authors. So we just simply consider an image as a discrete regular grid, dimension D. I call V the original image, and the denoised image that I call U is a convex combination of the original image where you select some pixels, and they are weighted against some weights, W. So that's here the averaging that is going to happen from some neighboring pixels that we need to find, and we also need to find the weights. So once you have the weights, then you simply do this average to denoise the image. The way we're going to search for those pixels that I call here T, they live in what we call in the original pattern, a searching window. So essentially, you want to denoise S, and then you're going to look at pixels T that are in a window as large as you can around S, so that you will find good candidates to perform this average. Now, this is the formula above to perform the averaging. Now we need to know how to compute the weights. So this is the original formulation of how we're going to compute the weights. What do we see here? what we see is that as follows. Delta, you should see it as a patch centered at S and another patch centered at T. What you do once your two patches are superimposed, you take the difference and you square it. And if you wish, you can weight each of these terms by a Gaussian kernel. And then you plug that into an increasing function. So in practice, this Gaussian term here, this Gaussian kernel, has very little influence on the result. So you should see it as a constant, and later on in the presentation, we're going to say it's a constant. So the similarity that is used originally in the annual means is the pointwise difference of the two patch. You square it, you sum, and you put it in an increasing function, for instance, the identity. So that is the measure of similarity that has been used for considering if two patches are close to each other in the original way. So the idea, again, of NL means is to do the weighted average that you see at the top, and the weights, W's, are computed using this essentially quadratic difference of two patches. So what we have in terms of complexity for the original method, if we assume that we have searching windows of size 2k plus 1 over D, so think about a big square of size 2k plus 1. If you have a patch of size 2p plus 1 power D, then the overall complexity to perform all those computations is proportional to the number of pixels. But you have an exponential dependence with respect to k, p, at the power d in the algorithms. So when d is small, it may look okay, but in practice, those k power d and p power d makes the algorithm potentially very slow. By very slow, it means that if you want to process, for instance, an image of size 4,000 squared, then it may take hours. And this is the performance of the original algorithm, and we want to reduce hours to a few minutes. That way, we'll be able to effectively use non-local means method without waiting too much time. So how we can improve the performance by a factor at least 100? So the idea is to leverage the parallel capabilities of modern CPUs, and to also leverage what we call vectorization. It means on modern computers, if you have, for instance, if you need to add two numbers or a series of two arrays, and then you need to add the arrays, modern processors are not taking the first entry of the array and the first entry of the second array and compute the addition. They're going to process the array by vectors. So they're going to collect the first 4 or 5 or 8 entries of the first array, the same amount of entries for the second array, and they're going to perform the addition on this array. The benefit of using vectorization is that the cost of addition or multiplication of two numbers, or the cost of addition and multiplications of two arrays, are exactly the same number of cycles on modern CPU. So here you have a speed up almost for free if you can vectorize your algorithm by a factor 4 15 years ago, 8 nowadays, and soon 16. So this is a key a key point of view, vectorization, that is crucial when you want to have performance in image processing. It's much more important than the number of cores that you have. That vectorization implementation is crucial for performance. In order to get a fast algorithm for NL means, the important point of focus is how we're going to compute the weights, WST, because this is where we have to spend time. The other operations are quite easy to do because they are linear. So this is where we have to focus, and this is where we can win. The way I'm going to describe how we can get that speed up is by considering, for simplicity, only a 1D image. Once we understand this, it is super easy to extend it to higher dimension, and the implementation is also straightforward. So I got my 1D image, so I can call that a signal, and omega, the support of the signal, are the integers from 0 to n minus 1. I got n pixels. The key quantity that we're going to use is to introduce this cumulative sum of the square difference of vk at minus vk plus the dx, which is a parameter given here. I square it, and then I sum. So what I'm doing here, I am doing a discrete integration of the square difference of the image v and its translation by the vector dx. This quantity can be computed in linear time. So this is a quantity that is very easy to compute in linear time. And now, assuming that we have computed this quantity, I'm going to show you how we can compute easily and efficiently the weights W. So this is the quantity that we assume or we have already computed. It's very easy. What I can do is to write again my definition of what the weights are. It is this formula. And now we're going to do very simple mathematics. We're going to do a change of variable for dx, that is t minus s. Then another variable p hat that is s plus delta x. And when you use these variables, then you see that the weight can be written as g of h. And now I got a sum. And then I see the vp hat and minus vp hat plus t squared. You work out the formula, you split the sum, you expand the square, and collect the data. And you arrived at this very simple expression for the weights. It's your nonlinear function gh applied at the quantity sdx that we computed before at s plus p minus sdx evaluated at s minus p. And using this quantity sdx that we introduced before, that can be computed in linear time, it means that we can compute the weights independently of t. And the key property is that it is computed in constant time, because I have access to the entries of SD in constant time, and then I can compute the difference, and I apply GH. And if you want to generalize on that idea to higher dimension, you simply repeat this process of the cumulative sum here for each dimension in another orthogonal basis. So what is the main upshot of computing data this way? So what we get is that what we need to do is 2 power d operations in this new formulation, and that quantity is independent of the size of the patch. So if you want to denoise images by averaging patches and you want to use the original algorithm, then you will see a dependence on the size of the patch forward the dimension. Using this version, then you do not see the dependence on the size of the patch. So this is already a big improvement in terms of complexity without using any parallel programming or vectorization. So the summary of the algorithm is as follows. We compute the cumulative sum of the image minus its shifted version squared. Once you have computed all these quantities, then you can use it to compute the square, the weights. And once you have the weights, then you can compute the value of the restored image. And you have to repeat this process for each possible dx. It means for each possible window that you are considering for doing the denoising. So this reformulation is somehow easy because it's about using the concept of prefix sums in computer science to compute SDX, this cumulative sum, and then simple algebra in math, expanding the square to get the algorithm. So what do we have in terms of memory compared to the original algorithm? Well, we pay a price. We have a better time complexity, but we have to use more memory. So this is the price that we have to pay. But now our new way of formulating NME's algorithm is that we can use many cores in the CPUs, or if you have many cores or many CPUs, then you can naturally do the parallelization. And as I was mentioning before, it's crucial for speed up and scientific computing to use the SIMD instruction. So single instruction that are operating not on one real number, but on multiple data. Think about an array. The cost of doing an operation on an array is exactly the cost of an operation on one floating point number. So you should see SIMD as a parallelization, but at the level of data. Parallelism originally is at the level of cores in a CPU, but you have also another level of parallelization in modern architecture at the level of data using SIMD. So we did implement our algorithm using SIMD, and we take great care to make sure that the code meets the specification of modern architectures. It's more about computer science, and I'm not going to detail that in that talk. What we get in terms of results, so using a computer created about 15 years ago-ish, what we see that when we increase the size of the image, essentially we multiply the number of pixels by 4, then we're going to multiply the processing time by 4. So we see a linear scalability here, as expected, and the code reacts exactly as it should. And now, this is perhaps the most important slide for this algorithm. It compares the serial version, the original NLP methods described by Morel and his co-authors, to process 8,000 squared cryo image. So essentially it took more than 2 hours. And if you are using our algorithm, when you are using 1 core, 2 cores, 4 cores, 8 cores, up to 16 cores, this is what we could do at that time 15 years ago, then you see speed ups from 23 by using exactly 1 core up to 100. Nowadays, We even have CPUs with even more cores, like 62, 64, 32, and so on. So we should expect even higher speedups for this algorithm. So as I mentioned, I think the key take-home message here is that using the algorithm that I just described, you can get on modern architecture and nowadays computers a speed up of 100 compared to the original version of non-local ints. So let me show you what we can do when we have these efficient filters in some applications in cryo-image. So here you see a cell of a bacterial protein where we expect to see some filaments. So when I zoom in the original image, I start to see a little bit of filaments, but it's very noisy. And after the filtering, I start seeing clearly the filaments that we expect to see. This is another cryo image that contains viruses. You have on the top left the original image, on the top right the denoised image. And when we zoom, on the left, you see the original image. On the middle, you see the result of the non-local means filter. And what you see on the right is that we keep reapplying the non-local mean filters on the output of the previous pass of the annual mean filters. So when you do it 4 times, then you start seeing those patterns. So people at Caltech, when they saw those images, they were happy because it met what they were expecting to see in terms of structures in those viruses. I also give you another example from another cryo image, where again, on the left, you see the noisy image, and on the right, after the enamine denoising, then we start seeing patterns involving filaments that people were expected to see. All right. So the take-home message here is that if you consider annual means, then there is another way to implement the annual mean algorithms as I just described, that is efficient, scalable, parallel, and vectorized. And the upshot is that you can easily speed up the original algorithm by 100s. And then I refer to that paper if you want more details. The algorithm that I presented is already available for several years now in several image processing libraries, and in particular MATLAB. However, as far as I know, the implementation that you have in those image processing libraries in MATLAB do not really leverage the parallelization, and they do not leverage the vectorization as we did. So you get a speed up, but certainly not 100%. Some people reported it was more like 8 to 10. It's not because of the algorithm. It's because people didn't implement it in the right way to leverage modern CPU architectures. So if you are interested in using these algorithms, I'm happy to share the code with you and even to adapt it on your own problem and see what we can do together. So again, feel free. Oops. Okay. So now I want to spend the remainder of the talk on trying to combine the idea of Morel using NL means and the idea of Stan of using total variations. So the idea is to combine those 2 points of view, the non-local point of view of NL means and the variational point of view, and especially total variation of the ROF model to preserve edges. So a general way to write down a total variation in a discrete setting is as follows. You consider any two pixels in your image. I'm going to say ui and uj. I take the absolute value, I put a non-negative weight, and then I sum those guys. The ij can be as far as you want in the image, or as close as you want. It doesn't really matter in this formulation. We say it's a general, non-local, specific total variation. And if you want to create a non-local version of the Rudinow-Shaffatemi model, then this is the energy that you want to minimize. You have a quadratic data fidelity with respect to the observed image V, and you have a general non-local total variation. Now, the whole point is, how are we going to solve efficiently these energies? And what I'm going to show you now is that we can optimize and solve exactly these optimization problems by using some graph and combinatorial techniques to map this original problem into graph algorithms. The upshot of doing that is you get extremely efficient algorithm that essentially runs in linear time in practice. And the result that you get, the minimizer that you get, is exact. It means you do not have an approximation of the minimizer. You have an exact one thanks to the combinatorial properties that these models enjoy and that we can leverage using graph algorithms. So in order to do that, I'm going to split part 2 in 3 parts. I'm first going to introduce a concept, the concept of minimal cuts in graph theory and how it does connect to binary or Boolean optimization. That will be a building block from combinatorial and graph theory that we're going to reuse to solve non-local TV optimization problems on arbitrary graph. And once we have this general version of TV, I'm going to show you how we can create special class of non-local TV using trees and that are useful for processing certain biological microscopy. So first, I'm going to use to introduce the min cut and the binary Boolean optimization. Okay, so I just want to give you a big picture of what's going on when we try to connect image processing, optimization, and graph theory. I'm first going to give you some definition that are a bit abstract, but then I will give you some figures so that you can understand in a graphical way. And then we're going to introduce a famous duality result between minimum cut and maximum flows. This is a result that is very useful for the computations. And then I will show you how we can connect optimization and what we're going to see. So the idea that I want to introduce, or the concept that I want to introduce here, is the concept of a cut in a graph. So I think it's better to simply look at the pictures below. You are given a graph with some nodes in gray, and we have 2 special nodes. One red that we call the source, one blue that we call the sink. And we have edges that connects the nodes. Now, the source and the sink are 2 special nodes. What I'm looking for is a cut. A cut means that I'm going to remove edges so that one node, let's say that node in the middle in gray, is connected only to the source or only to the sink. So here, in that cut, that node here is connected to the source. The node P is again connected to the source, same for Q. And here, I show you a node that is connected only to T. So cut means that you remove edges so that after you remove the edges, then one node is connected either to the source or either to the sink. In other words, what you are looking for is a partition of the nodes so that we assign each node to the source or to the sink. And this is what a cut in a graph means. Once we have a cut, we can say, okay, I'm going to associate numbers on my edge, on each edge, and those numbers, I'm going to call them Cij. So now, every time I have an edge that is in the cut, I can associate a quantity that we call the capacity of the cut that simply corresponds to all edges that start from a node that is in the source that goes into the sink. And if I have such an edge with a cost Cij, I put it in the sink. And so this is a quantity that is defined for every cut in a graph, and that is called the capacity of the cut. Now, the idea is, can we minimize the capacity of a cut in a graph? And this problem is called a minimal cut in a graph. So far, this is a graph theoretical problem, and let's see what we can do. Well, you have the following results that is famous in graph theory that tells you that if all the capacities in the graph are non-negative, then you have a duality theory theoretical result due to Ford and Foucaulson. This is essentially what you read in textbook in graph theory, but it turns out that Shannon and his co-authors developed exactly the same result the same year, but most people forgot. And they tell you that finding the minimal capacity among all cuts in the graph is equivalent to a special kind of linear program that is called the maximum flow in the corresponding graph. So here, just for to be comprehensive, I write the maximum flow. It's a linear programming, a special kind of linear programming problem. And the key upshot of this result is as follows. We do not have, as of today, good algorithms to compute minimum cuts. We just don't know. Maybe the efficient algorithms exist, maybe they don't. However, we have very efficient maximum flow algorithms. So when we want to compute a minimum cut in a graph, we compute the dual problem thanks to this theorem. It means we compute the maximum flow, and once we have the maximum flow, then we can compute easily the cut. That slide is simply to tell you that the computing maximum flows is well-known problems that have already very efficient algorithms. It's been developed in the last 60 years. And I'd like to mention that for image processing, Boykov and Kolmogorov in 2004 developed a very efficient maximum flow algorithms for computing cut in graph that arise from image processing and computer vision algorithms. In practice, the time complexity is linear. It's much better than the theoretical complexities of others. The worst case for the Boykov and Kolmogorov algorithm is exponential. So in terms of theoretical complexity, it would be a terrible algorithm. But we don't know why it runs so fast for all problems that we are dealing with in computer vision and image processing. It runs in practice in linear time. So this is one of the big mystery that puzzles me at night sometimes, why it is so efficient. The good news is in practice, every time we run it, it's linear. So how do we connect these graph algorithms into binary optimization? Because we want to optimize TV. So here, instead of shooting for TV, I'm going to shoot for Boolean or binary optimization. And actually, it turns out that this construction has been done, by Picard and Ratcliffe in the 70s. And it started even before. The idea is as follows: how to connect cut in graphs and optimization. In order to connect to optimization, we're just going to introduce binary vectors. And I'm going to consider binary vectors where the first entry is 1, the last one is 0, and then I have n other entries denoted by x1 up to xn. And now I'm going to make an identification of these binary vectors and a cut in a graph. And I'm simply going to say the first entry of this vector corresponds to the source of the cut that I want to do in the graph. And if I am the source, or I am connected to the source, I'm going to assign the label 1. If I am the sink or connected to the sink, I'm going to assign the value 0. So every time you have a binary vector, meaning each entry is binary, 0, 1, you are making an assignment for each node if they are connected to the source or if they are connected to the sink. So it means that each vector is actually a representation of a cut in a graph. So instead of considering nodes, you consider binary vectors, where each entry of this binary vector encodes the fact that a node is connected to the sink or connected to the source. And now, once you have this identification, it's simply a matter of rewriting the previous formulas using our new formula, new symbols, x1 and xn. So, for instance, the capacity of a cut, where now the variable is big X, it's a vector, corresponds to all points that are connected to the source, it's xij, and where I have an edge that ends up in the sink. So to be in the sink means xj is 0. So when xi is the source, I am 1. When xj is in the sink, then I am 0. And then it means that that quantity, that product is 1. And I multiply it by the cost of the edge, Cij, and I sum. So now I have an algebraic representation of what the cut is in terms of binary vectors. So now you do again the simple algebra, remembering that we deal with binary variables. So it means that when you square a variable, then you get the variable itself. You have this identity, x squared equals x. And you simply expand this term here using this calculus rules. And then you get the following representation in terms of binary polynomials. You see a constant, you see a linear term, and then you see a quadratic term. And you can go forward even more. And now you say, this is the formula that I have that corresponds to a cut in a graph. And now I ask the question, well, I consider a function f of x, that is a constant plus a linear term plus a quadratic term. Under which condition c and f are the same? It means, can I build a graph so that my function f that I want to optimize will be exactly the capacity of the cut in a graph? And the answer is yes, you can construct this graph. So every time you are given a binary function that takes this form, then there is a way given by Picard and Ratcliffe in 75 to construct the graph and the capacities such that the capacity of a cut in the graph will be exactly the value of the function that you want to minimize. So what you get using this point of view is that if you want to minimize f, then you don't, all you need to do is to build the graph and compute the minimal cut. If you have a minimal cut, then it means that you also have a f, and then you are minimizing this function. It's the equivalence. So now, in order to have efficient algorithm, the condition that we need to have is that in this quadratic term here, we need to have minus Qij, and Qij has to be positive. So it means the coefficient in forms of xi and xj has to be negative. This is the condition to have efficient algorithms so that you can leverage the duality between min cut and maximum flux. Okay, let me skip that. So now I have my computational building blocks. I know how to minimize, under some assumptions, binary energies. My original goal is to minimize total variations. Total variations on images, I need to find a vector in Rn because I'm considering here grayscale images. So how am I going to connect a minimization on Rn with a minimization on Boolean values? This is what we're going to do. So this is a recall of what is the non-local AOF model with the quadratic term. And here I'm simply going to generalize just a little bit, where I'm going to replace the squared here by a more general convex function D. And this is the quantity of interest. In particular, if D is the quadratic, you recover the AOF model. So again, how are we going to connect this optimization problem here to binary optimization? And now this is where math is beautiful. Fleming at Brown, more than 50 years ago, 60 years ago now, developed a formula for total variation that connects the original formulation of total variations. In continuous world, this is what we would write, an integral of the L1 norm of the gradient. This is a non-rigorous way of talking about TV. And that sum here can be seen as a discrete approximation of that integral here. And what Fleming and his colleague proved is that value of the total variation is exactly the same, the following quantity. You take your function, or you take your image u, and you threshold it at some level lambda. That gives you a set. Now, on this set, you compute the perimeter of the lower level set of u at lambda. And you integrate all those parameters when the threshold is going to move. And what Fleming and Richel proved in that the total variation on the left is exactly the same quantity on the right. And that formula is called the Coll formula in functional analysis. And this is what we're going to leverage to make the connection between optimization of non-local total variations and binary optimization. So just quickly, for some notations, I in the site of a pixel, UI in the value. For simplicity, I'm going to discretize the gray level of the image because it simplifies the presentation. I only need 3 slides to do it. Otherwise, it gets more technical. But you can easily extend what I'm going to present here when UI is a real number. And you are given a set of interactions between any 2 pixels, and then you choose. The key property, the key concept to do the reduction to binary optimization is to introduce the level sets of the image U that is supposed to be the minimizer. So I'm going to consider the level sets of U. U is the variable in my optimization problem. I'm going to threshold it at the level lambda, and it's 1 if I am less or equal to lambda, and 0 or otherwise. And the key idea here is that instead of considering U as the variable that I need to optimize for, I'm going to consider the U lambda. It means I'm going to consider the level sets of the U lambda function. And what we need to do is to formulate the data fidelity term and the TV term. So the way we do it is for TV is by using a discrete version of the Coll formula. I got my non-local TV. I can write it as an integration, so here a sum on the gray level of the perimeter of the level sets of U and the level lambda. You replace the formula, then this is the new formula that you get on the right. What you see is that you do not have U anymore, you have only U lambda. You do the same for the data fidelity. Now, you should see this quantity as a discrete integration of the discrete derivative of the data fidelity. It's the analog of the fundamental calculus theorem, where you integrate the derivatives. And again, what you get is you are able to express the quantity on the left only using the variables U lambda. You plug that together, the original energy that you want to optimize can be written as follows. It's a sum of binary energies that are associated to each level lambda at which you do the threshold. So it's a sum of binary optimization. Now, let's go wide, and let's say that we can minimize independently each of the term in that sum. Let's go wide. Let's do it. So I minimize each of my binary energies. I get for each level lambda a binary minimizer that I call U hat lambda. And the idea, if everything works, is to use the following reconstruction formula for defining the solution to the original problem. So essentially, I'm going to use the smallest possible value of lambda such that U lambda is 1. That way to proceed only works if the family of the level sets U hat lambda defines a function. In order to have a function, we need to have a monotone property. It means that essentially the function must be single valued. It cannot be multi-valued, otherwise it's not a function. And then we have a result that says yes, under the assumption that essentially the data fidelity are convex, which is assumed in this work here. For instance, the data fidelity could be L1, could be quadratic, or could be any convex function. So any convex plus TV models will satisfy the assumption of this theorem that tells you that you have the monotone property, meaning that you can minimize independence. So what we can do right now is simply to apply the optimization algorithm for binary energy that we saw, and we're good to go. I just want to tell you a smart way to do the optimization, because if you do the binary optimization level by level, then we're going to call L-1 maximum flow or min cut, which is very costly. There is a much better way to implement the optimization of this sum here, is to use a divide and conquer approach. So let me tell you briefly how you can proceed. You first solve your binary optimization problem at level lambda. Now, for each pixel, you know if the optimal solution is less than lambda or more than lambda. So let's say that that part here is less than lambda, and the other one are more than lambda. We compute the connected components, and then we say we're going to minimize independently each of them. Why can we do that? This is, again, where the CryoElectron formula comes in. When I want to optimize for this problem here, I need to know what the value should be, for instance, for a pixel here at the border, what the value of the pixel should be on the left. Why? Because I have my TV. So let's say I want to optimize for UI lambda, but I need to know what the value of the neighbor should be, uj lambda. That is not part of this new problem. But think about it. We already know the value. Since we have the decomposition, if that guy in the CC, we know it's less than lambda, and otherwise it is greater than lambda, then we know that that value here, the uj lambda, is 1. So we already have the value. So it means that when you do this decomposition and we solve problems independently, there's no problem, because every neighboring pixels that are not in the current connected components, we already know the value. So it means you can repeat the process on smaller and smaller graphs, and then you recompose the solution. And instead of doing L maximum flows, now you only do a logarithm of it. Let me show you, skip that because I'm running late. The idea here in this table is that this algorithm is very efficient. And when we increase the size, when we multiply by 4 the number of pixels, we multiply by 4 the number, the time to execute the algorithm. So in practice, we run in linear time to minimize TV of the form that I described before. Okay. So now, in the last 5 minutes, I want to give you an idea about how we can use these algorithms for processing some biological microscopic image. I want first to show you quickly on a toy example what's going on when you do TV on this toy example. So you do RF model, and you see 2 things. You start losing a bit of the contrast. You see the square in the middle is darker than the original one. And then you see that instead of having perfect squares, now we are starting to smooth the corners. One of the questions here is, how can we mitigate the loss of contrast? Well, then we know we're going to replace the quadratic by a L1 term. So this is what we're going to consider for the data fidelity. And now the question is, if I really want to preserve the edges of the square, or think about images where you have a really long and thin structure that you want to preserve. How am I going to do that? And the idea is to consider non-local interactions by changing the topology. And the topology that we're going to use is going to be introduced by the image itself. Let me give you an example of how we're going to do that. We're going to consider the level set of an image. We have the lower level set, the upper level set. It is well known that upper level sets and lower level sets satisfies an inclusion properties. And from these inclusion properties, you can create trees. So if you are considering lower level sets, you are considering mean trees, and means you prefer dark objects on light background. And otherwise, in the case of upper level set trees. You can merge these two trees into a single one using what we call the fast level set transform introduced by Monas. And the idea to do the merging is to introduce the concept of holes. So you can merge these two trees if we're using holes. Let me give you a brief example of what's happening on a simple example. This is the image that I have. And from this image, I can consider shapes that are the connected components of level sets where I fill the holes. I still have an inclusion property, and then it means I can associate a tree to this image. And now I can use these level set-based trees to encode the topology that I want in my image. And this is what we're going to do. We're going to minimize TV, not on the using the nearest neighbors interaction on the grid, but on the tree, using the tree. How you do this? Well, I want to minimize L1 TV on the tree. I need the following quantities for each node in my tree: the GUI level of the parent, the size of the connected components, and the perimeter. Once I have this quantity, I can define the L1 data fidelity for each node in the tree. And I can also define the total variation on that tree, similarly to what the core area formula was for the general TV. We proceed as before. And you end up with trying to minimize this optimization problem. And we can reuse the algorithm that I showed for TV, because it doesn't really matter for the combinatorial-based optimization if you have a grid, a tree, or a general graph. The algorithm will work the same way. So it means we can reuse our algorithm. And let me skip this and to show you directly what you can do with this algorithm on an unsustained histological section of a mouse brain. The idea, again, that problem was originally from Alex, where the idea here is you have a collection of these brains, and you have two problems. The first problem is to do the registration of two slices of this brain in a precise way. And also, you want to estimate some properties of those tissues, and for that, you need to solve PDEs on those guys. So the goal here is to create a triangulation of this image here, so that we can do both the registration and both the numerical solution of the PDEs that we want to put on this brain. So this is the original image. This is the image that we can obtain using the fast level set transform plus TV, where essentially we were able to extract all the textures while preserving the very long and thin structures that were crucial for the application. And from here, we can zoom in and see that, well, since I used level set trees, I removed some noise, but my boundaries will be noisy because I used a strict connected component algorithm to define my topology. In order to get the edges, you simply need to use a canny filtering, and then you get a very precise boundary of where the edges are. And once you have these edges, then you can run triangulation algorithms. And the triangulation that we got here to represent the original image that we have here contains only about 2% of the original pixel of the information. And again, you can use it to match features, to solve PDEs, and so on, because you have the triangulation. Okay, let me skip that. And let me conclude this part here. We can effectively combine ideas of non-local means with the variational methods for TVs, and we have efficient, super efficient algorithm to minimize all those non-local total variations. I still believe that changing the topology for the task of interest is a great way to think. I only considered in my research the level set based approach that I just presented to you, but I firmly believe that there are other topologies that should be explored for other applications. It's changing the topology. We know from NN means that this is a very powerful tool for applications. And here I give you the reference for that paper that describe these results. And finally, I want to give you the summary. So now we have non-local means algorithms for microscopy. You can leverage modern CPU architectures to implement them. And I just want to mention what's going on next. Because once you have a 100 speed up, you may say, okay, it's done. And then we move on. Yes, this is what has been happening essentially for the last 15 years. But nowadays, we have other technologies for doing computations. I'm thinking in particular about FPGAs. So FPGAs is a new kind of technology originally created in the 80s in research, and then some companies started to send those guys. But it's only in the last 5 years where we have adequate software to program them and to have access to these FPGAs in a reasonable way. The main upshot of using FPGAs compared to CPUs or GPUs is that they offer much more parallelism and much more efficiency than CPUs. So for instance, I've been using FPGAs for solving optimal control problems, and I get a speed up of 10,000s, not 100, not 1,000, it's 10,000s compared to GPUs or CPUs, with only a fraction of the energy to run CPUs and GPUs. That's why Intel bought a few years ago the second largest companies for $15 billion. AMD bought the largest one, Xilinx, last year. I mean, it became official this year for $30 billion. So I still believe that we should leverage this new technology that requires very little energy compared to GPUs and CPUs. And I've been talking with Stan about exploring FPGAs for non-local TV. And I insist, I'm happy to answer your question. Feel free to contact me if you need some code. And I'm happy to rewrite and adapt the code that I have for your own application. Thank you.